Okay, so today we're going to talk about parametric equations, and we're kind of going backwards. It's fine. We're going back to 10.6, but I think it's actually going to be helpful. So parametric equations is a set of equations that involves a parameter. So F and G are continuous functions. So you don't really need to write that. And we have a ordered pair that we can find coordinates on our curve. Okay. So the equations X equals F of T and Y equals G of T are called our parametric equations, where T is the parameter. So these are called parametric equations because they involve a parameter. We now have a third variable. So we have X equals something in terms of T, Y equals something in terms of T. So we're plugging values in for T and getting XY coordinates. I'll explain what that looks like when you get written down what you need to, but I at least need you to write down that X equals F of T, Y equals G of T are our set of parametric equations where T is the parameter. Okay, if you don't write any of this, that's fine. FYI, today and tomorrow, this 10.6, this is the portion of the test that will be with a calculator. So everything that we did on our quiz yesterday was non-calculator. That will be like the first part of your test. The second part of your test will all be from 10.6, and it'll be with a calculator. Okay. All right. So what's the point of this? Okay. Well, let me show you something, okay? Here is a rectangular equation that I've written as a set of parametric equations, and here is the parametric graph. What do you notice about the graph that we don't normally see? Thank you. What does the graph have that you don't normally see on a graph? Yeah. Okay, our graph has these arrows. Okay, when we plug values in for T, we're going to plug values in for T in an increasing manner to where we're going to plot points, and our graph is going to have a certain orientation. It's going to have a direction. Okay, so one thing that we're going to get to do with our graphs is we're going to indicate the orientation. Which way is this graph being drawn? Okay, we're going to have arrows that follow one direction. We're not going to put like two arrows that go infinite. We're going to have to go in one direction. Okay, now since T is our parameter most oftentimes, what do you think that we could like move forward and use T to represent? T could represent something in an application problem. What word starts with T? Time. Tomorrow, we're going to look at parametric equations where T represents time. Today, T is just going to be normal. Okay. So here we go. Let's talk about how to graph a parametric equation. Are you ready? Okay. Go ahead and write down this right here. XY axis, yes. Now, in this scenario, I am giving you the values of t I want you to plot. Okay. So what we're going to do is we are literally going to just make a table of values. We are going to plug in a value for t. And when we do that, we're going to get an x, y coordinate. Okay, so help me out. When we plug -2 in for t, let's come up here to x equals t squared minus 4. What do we get? Help me out. What do we get? 0. And when we plug t as -2 into this y equation, y equals t over 2, what do we get? Okay. Now let's plug in -1. When we plug -1 in for t, what is our x coordinate? And what is our y coordinate? Then we're going to plug 0 in for t. When we plug 0 in for t, our x coordinate is -4. Our y coordinate is, thank you, Grayson. All right, let's plug in 1. Oh, and what do we get for x when we plug 1 in for t? T squared minus 4 when we plug in 1, minus 3. Okay, how about for y? Finn, what do we get for y when we plug 1 in for t? Okay. T equals 2. Valerie, what do we get for x when we plug t equals 2 in? Okay. And then our y coordinate, Joby, what would it be when we plug t equals 2 in? Okay. And finally, t equals 3. We would get 5 3/2. Do you agree? Okay. So we're going to plot our points. And what I did is I plotted them in the order in which I found them. So from the smallest t value to the greatest t value. And as t increases, this is what happens to our curve. So I am going to indicate the orientation by adding those arrows based on my smallest t to my biggest t. This is how I connected them. So that's the direction my arrows need to go. Give me a couple arrows and we're good. It matters the direction of the arrows, but I just need a couple of them to indicate which direction we're going. I mean, make it look aesthetically pleasing. Don't like stack them right next to each other. Spread them out. Was that difficult? Can you do it? No, we can't do it. Okay, can you do it, Owen? Okay, now in this problem, I gave you start at -2, stop at 3. Here's our second example. Do I give you that? No, write down your second example here. And I want you to start thinking about where we should begin our T, X, Y chart. Probably not. No. Probably not. No. All right. So does anybody have an idea about where we should start our T XY chart? Why? Okay. Are there numbers I can plug in? I can plug in 1. What else can I plug in? How about this? What can I not plug in? Yeah, you could. We can't plug in negative numbers because we have x equals radical t. Okay. So the smallest number I can begin to plug in would be what? 0. I could plug in 0, and then I could plug in 1, and then I could plug in 2, and then I could plug in 3. Okay. So when I plug in 0, okay, when I plug in 0, we get the square root of 0 and 0 plus 2. When I plug in 1, we get the square root of 1 and 1 plus 2. Now, Grayson, can we plug in can we plug in 2? Yes. Do we want to plot square root of 2 comma 4? That doesn't really sound like we could do that very accurately. So we could plug in 2, we could plug in 3, but wouldn't it be a lot easier if we plugged in 4 next? Just because we have that radical t. I mean, is that okay? Okay. So we're welcome to say, all right, when we plug in 2, we get radical 2, 4. When we plug in 3, we get radical 3, 5. When we plug in 4, we get 2, 6. That's the point I'm going to plot. Okay. What does it look like we're about to draw? A full parabola? Like a half of a parabola, right? And as we draw this half of a parabola, we need to indicate that we started here and our coordinates built in this direction. Our t value is always getting bigger. And as the t value gets bigger, we plot points, and that arrow indicates the direction of those points being plotted. Did that answer your question?
Kind of, but like, how is it any different than anything we've done? Just making a table about it.
Because we have to go in a certain order. Yeah, that's the biggest difference. Now, how many of you think that this could get tedious if I asked you to do this every single time? Especially if I gave you one that didn't have a domain restriction. Okay, that could get old. Okay, so we can do something algebraically called eliminating the parameter, to where we could take a set of parametric equations and squish them together and write it as a rectangular equation. Okay, so that's what we are going to do next. Okay, we're going to take a set of parametric equations and we're going to write it as one rectangular equation. So one equation with x and y. So to do that, you're going to solve for t in one equation, throw it into another, and then simplify and make it look pretty. It's substitution. We're not like solving a system. We're taking two equations and squishing them together. So substitution is the only way to go. So what we're gonna do is we're gonna go back to the two examples that we've already graphed. And we're gonna go back to those equations and eliminate the parameter. And we'll go back and look at how that relates back to the graph. Okay. Make sure everyone gets written down what they need. All right, so we'll go back to this very first graph that we have. We're going to eliminate the parameter for this set of parametric equations. Okay, there is no wrong way of going about choosing whether to solve for t in x or y, but there's always, not always, but sometimes there's a way that is easier or makes more sense algebraically than the other. So if we look at these two equations up here, what might be the easiest one to solve for t in? Y. If we solve for t over here, we're gonna have to like square root and do plus minus. Let's not do that, okay? So we could say that 2y equals t, right? So then we can come over here, put that 2y squared minus 4 equals x. So x equals 4y squared minus 4, right? We've totally gone through our conics chapter already, right? And we're gonna have to take our final pretty soon. So let's just go ahead and take this and put it into standard form. So we can add the 4 over. And then we always want the coefficient to be with the non-squared variable. There's our parabola that we graphed. I'll come right back. Right there. Does that look like a parabola with vertex -4, 0 and a p-value of like 1/16? Yeah, sure does. Okay, if you get to here, I'm pretty happy, but getting to here is the standard form of the parabola. Okay. All right, let's go back to that second one that we graphed. This one right here. Here again, I think that whichever one we choose, it's probably going to be the same amount of work. Okay, so how many of you look up there and you want to solve for t in the x equation? Okay, how many of you look up there and want to solve for t in the y equation? How many of you have no care in the world? Okay, so 5 people have opinions today. This is rough. Patton, what do you want to do? Okay, so y minus 2 equals t. That's what you like to do. And then we can take that and throw it in here. So x equals the square root of y minus 2. Why? Why? Because then we can write x squared equals y minus 2. Why is that bad? Okay, let's do it the other way. x squared equals t. So y equals x squared plus 2. That probably was easier. Hey, both ways we get y equals x squared plus 2. And let's go back to our graph. Does that look like y equals x squared plus 2? Half of it, right? Okay, so something we are going to have to be aware of. Right here, we know that t has to be greater than or equal to 0. Well, because of that, since t can only be 0 and bigger, what's going to happen with our x coordinates? They are only going to be 0 and bigger. So we have this y equals x squared plus 2, but we also need to let them know that we have a domain restriction. Okay, so there's our equation, but also x has to be greater than or equal to 0. Okay, write this down. Y equals 1. How is that y equals 1? No. Okay, so you would like to solve for you would like to solve for t in the x equation? I feel like we all need to just realize that that's the better option, right? In this case, it's really the only option. I don't want to solve for t over here, do you? Okay, so you're saying t over x, but then we also have to replace t, right? Okay, so, but that's essentially what we're going to do, Nick. So let's just make it official and say that t is x plus 1. So then when we take t and we plug it in over here, we get y equals x plus 1 over x. Do we have any domain restrictions for our parametric set? Oh, t cannot be 1. And if t cannot be 1, what is that true about our domain? X can't be 0. Okay, so here we have eliminated the parameter. Okay, well, here's how this is going to help. Instead of me plugging in a whole bunch of values for t, I can graph this parametric equation based on this rectangular equation we just came up with. What are we working with here? X plus 1 over x. What kind of graph is that? It's a rational graph where, since 0 makes our denominator 0, we have a vertical asymptote at x equals 0. Since our degrees are the same top and bottom, we have y equals 1 as a vertical asymptote. And here are our graphs. Ooh, what am I missing? arrows. How do I know where to put the arrows? Okay, let's just plug in some numbers. What happens when I plug in 1? We would be, oh, we can't. What happens when I plug in 2? We would be at the coordinate 1, 2 over 1. Okay, if I plug in t equals 3, I'd be at the coordinate 2, 3/2. Okay, well, I need to go from t equals 2 to t equals 3. So our orientation is going to be this way. What's the problem? Okay, I know that it's been a while since we've grasped something like that. Okay, I'm more concerned about our parabolas and our ellipses and lines and things like that. But you may have one of these on your homework, so just be ready for it, okay? Okay, last one. Ooh, I like this. Every once in a while, we're gonna have a Greek t, theta, instead of t for our parameter. Isn't theta a Greek letter? Okay.
It's supposed to be a joke.
No, but you're like, it's a Greek letter. So you want to solve for theta in one of these to eliminate the parameter? That's really not going to be enjoyable. Don't write this down. We could have x over 3 equals the cosine of theta. So theta equals the inverse cosine of x over 3. And then I come over here and put it in, and you have 4 sine of inverse cosine of x. Ew, no, 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 no. I could do something with this. Do we have anything in our toolbox that relates sine and cosine together? What else? I don't see tangent up here. Tangent, not gonna be helpful. What else relates them together? Do you agree that cosine squared plus sine squared equals 1? Okay, so if cosine squared plus sine squared equals 1, and I can solve for cosine and I can solve for sine, cosine of theta is x over 3. Sine of theta is y over 4. What do we have? We have an ellipse. Have an ellipse. Uh, 10A. You took your test like last week, right? Or a week and a half ago, right before our long weekend. Okay, this ellipse, vertical or horizontal? Vertical, where A is 4, B is 3, but since we have a parametric equation set, our graph must include Okay, so I'll let you get caught up with what we have so far, but we need to indicate arrows. We need to indicate our orientation. The best way to figure out your orientation after you've eliminated the parameter is going back to the original set of parametric equations and plugging in two values. So when I plug in 0 for theta, I would get 3 cosine 0 and 4 sine 0. So we would get the coordinate 3, 0. Okay. If I plug in pi over 2 to theta, I would get 3 cosine pi over 2, 4 sine of pi over 2. That would give me the coordinate 0, 4. So here's my coordinate for 0. Here's my coordinate for pi over 2. So it looks like we're going in a counterclockwise rotation to draw this ellipse. Okay. So you have like 3 things you're going to need to do in the homework assignment. You're going to need to make a table of values to graph. You're going to need to be able to eliminate the parameter, and you're going to need to be able to graph after eliminating the parameter. So those 3 things you need to be able to do in your homework tonight. People, this is your last book assignment.